All right. So if I'm looking at this problem, it's asking me to graph and label the equations. And then if I scroll down, it's asking me for the solution. So let's just deal with the first part. To graph and label, we know we have two methods. I'll do one way and one the other way. So if I look at the first equation, I know that I can use my slope and my y-intercept to graph. My y-intercept is always a free point of 0, 2. And my slope, I can use rise over run, which tells me to go up 1 and over 2. So if I go to my graph and I go to 0, 2, I can go up 1 and over 2, up 1 and over 2. And these would be my points. I can go ahead and add my line in. Slightly off, but it's all right. Make sure I add my arrows and I label my graph. And for the second equation, I can do the same thing, or I can make a table of values. So if you don't remember either method, I'm going to show you ways that you can do it. So I'm just going to substitute into 0 into the equation, which is going to give me -1. I'm going to substitute in 1 minus 1, which is going to give me 0, and 2 minus 1, which is going to give me 1, 3 minus 1, which is going to give me 2. And I'm even going to go a bit further and do 4 minus 1, which gives me 3. And last one, 5, 5 minus 1, which gives me 4. So now I have some values that I can go ahead and put on my graph. So 0, -1 is going to be somewhere down here. And 1, 0 is somewhere over here. We'll fix that and make it a little bit neater. 2, 1 right here, 3, 2 right here, a little bit higher, 4, 3 right over here, 5, 4 right here, and I can go ahead and put my line in for this graph. I'm going to add in my arrows, and I'm going to label my graph. So I use both methods. We can see that this has a point of 1 solution, but I can't exactly see the solution because of how the graph is scaled. So I'm going to scroll down and I'm going to solve y equals 1/2 x plus 2, y equals x minus 1. So the easiest way I see to solve this is because they're both equal to y, I can set them equal to each other, which is a method of substitution. Make this a little bit better. So 1/2 x plus 2 equals x minus 1. So I'm going to subtract 1/2 x from both sides, extend my page. This side cancels, minus 1/2 x from this side. And I'm going to be left with 1/2 x. I'm going to bring down the -1 and also bring down the 2. I'm going to add 1 to both sides because I'm trying to isolate x. I'm left with 3 and 1/2 x. Divide 1/2 by both sides. Divide 1/2 by both sides. So x equals 6. So after I found x, I know that I still need to go back and solve for y. So I'm going to take my second equation, y equals x minus 1, and I'm going to substitute in a value for x, which we now know is 6 minus 1, so y equals 5. So my solution to this equation is going to be 6, comma 5, and that is one solution. That is the point of intersection. We want to go back up to our graph and make sure that we are somewhat accurate. Our lines are a little bit off, but 6 comma 5 would be somewhere around here. So we're slightly off, but that is the solution because we solved it mathematically, algebraically. All right, next problem. Next problem. Does the equation below define a linear function? Well, there's a couple ways to think about this. We always know that x is raised to the power of 1 in a linear function. And a linear function also has a constant rate of change. So here I know my x is raised to a negative 1 because of my exponent rules, and x is in the denominator. So I know this tells me this is not linear. I can also create a table of values to see if as x increases by 1, and x cannot be 0 in this case, as x increases by 1, does y show a consistent pattern? So 3 over 1 is going to give me 3. 3 over 2 gives me 1.5. And 3 over 3 using the equation gives me 1. So you can see here that the difference between 3 and 1.5 is minus a 1.5. And the difference here is minus a 0.5. So this does not show a constant rate of change. Just erase some of this so you can see. So we had a negative 1.5, and then a negative 5. There's no constant rate of change. So this is not a linear function because there is no constant rate of change. All right. And the next problem. All right, let's stop here.